is today. So that's up and live. So make sure you do that. It's going to be on KW, and then identifying an acid and a base, acid-base strength, looking at Kas and stuff. So anyways, that's today. And then the chapter 10 homework, I hope that you are consistently working on that a little at a time. So today we're going to cover how to calculate pH, and then how to calculate pH of a buffer solution and what buffers are. So after today, take some time to go through the homework and work problems where you're having to solve for pH. Again, maybe it's 5 or 6 or 7 of them, I don't know. But that will help keep you from really stressing about it and having a ton to do next Monday. We just finished a kind of a little review on chapter 9 during my office hour, and that is recorded. And so when I get the email that Zoom has it ready for me, I'll download it, process it on YouTube, and post that. So we worked several different kinds of problems with chapter 9. We didn't get to everything in chapter 9. So we did not get to things like osmosis or equivalence or looking at solubility graphs and stuff, but we covered some problems and I think it was good. So make sure to check that out. And then Monday from 8:30 to 9:30, I'm going to do a review on chapter 10. And then from 10 to 11, I'm going to do an identical review. So pick one of those times if you can and join us. I think you're going to need it because, and I'm going to record that and post as well. I think you're going to need it because today we have just more content than we're going to get to. So unfortunately, there's a huge thing I wanted to get to and we did not get to it. But if we don't start now, we're going to already be behind. Any questions from you guys before we get in? Okay. All right, here we go. If my screen will connect. pH. All right. So here's where we here's where we ended. I just have to show it again. It's just the best. Stupid horse. It makes me laugh every time. Here's where we ended last time. And you're almost there. You're almost the end of the semester. Here's where we're going to start. So pH. We started talking about how do you decide if a solution is acidic or basic. And double check that you're on mute. And we're going to continue, but we're actually going to use pH scale today instead of all these numbers. Remember, we were looking at these really crazy exponents, okay? We said something is acidic or basic depending on its concentration of H+. All right. We said if H+ or OH- is equal to 1 times 10 to the minus 7, that's neutral. Okay. And then if it varies from that, depending on how it varies, it could be acidic or basic. But these numbers are really small, right? Like if I ask you a question, which one's larger? This becomes kind of awkward. It's awkward to use molarity because it takes a minute for my brain to look at that number and be like, all right, 8's bigger than 7, but it's a negative exponent. So 10 to the minus 8 is actually small. It's anyways. So that's why we use pH. Okay. pH is nice numbers between 1 and 14. All right. And that's easier for us to look at a number like that and make a conclusion than these crazy exponents. So we're going to use pH scale. P is a mathematical function. It stands for the negative log of something. All right. So you have a button on your calculator, negative log. And you're going to use that button a lot today. Okay. So if we do the P of H, what that means is we're taking the negative log of the concentration of H+. Okay, so that's what pH is. We have an equation for pH. It's the negative log of H+. But we can apply this function to anything. Okay, we could say the P of OH because we know there's been times we've had to calculate the concentration of OH, right? So P of OH would be the negative log of the concentration of OH minus any number. We could apply this to any number. Ka. We had all these different Ka values for acids, right? So today, later, when we get to the buffer problems, we're going to have pKa, which is just we took the negative log of the value for Ka, for the weak acid. All right, so again, P can be applied to anything. It's just a mathematical function. So considering all that, are the following concentrations of H+, let's classify them as acidic, basic, or neutral based on what the pH is. Well, you could actually classify them based on the concentrations we see here. So let me scroll up and remind you. I'll be right back. Right here. Here's where we define what is acidic. We said if H plus concentration is greater than 1 times 10 to the minus 7. If it's equal to 1 times 10 to the minus 7, it's neutral. If it's less than 1 times 10 to the minus 7, it's basic. All right, so remembering that from what we talked about Tuesday, let's go down here and look at this. So we have 1 times 10 to the minus 7. So is this acidic, basic, or neutral? This is neutral. And what is the pH? So how do we calculate this? We just do negative log of 1 times 10 to the minus 7. So grab your calculators today. What is pH? What'd y'all get? Okay, yeah, in the chat, 7. Okay, what if you have a concentration of H plus where it equals 1 times 10 to the minus 9? What is that? Is that acidic, basic, or neutral? That is less than 1 times 10 to the minus 7. So, yep, Keegan said it's basic. Okay. And if we do negative log of this, all right, 10 to the minus 9. If we do negative log of this, what do you get? pH equals, yep, Haley got it, 9. Are you noticing a trend? What's the trend? pH equals the exponent, right? So far. Yep. So 1 times 10 to the minus 4, this is greater than 1 times 10 to the minus 7, so we should say this is acidic. And so negative log of 1 times 10 to the minus 4, that is a pH equal to 4. Okay, so far we're seeing, all right, seems like the pH equals the exponent. Is this always going to be the case? I wish I could tell you yes, but no, it won't always be the case. So when is it going to be the case? I'm going to keep what's visible on the screen, but right down here below on the next slide, if the H plus concentration has a base number of 1 times 10 to the whatever, then we can say pH is equal to your exponent y. But if the base number isn't 1, if it's like 2.3 or any other number besides 1, you cannot keep this fun little rule. It's not that simple. So what if it's not 1 times 10 to the minus? What do? Just plug it into your calculator. Okay. All right, any questions so far? So on a pH scale, how do we make sense of these numbers? You probably are familiar a little bit with pH scale, but I'm just going to remind you, pH runs, if you look at this figure, I'm going to use my blanket, 0, 1, okay, these low numbers, pH of a 0 or 1. Really, we don't really hardly ever see a pH of 0, but pH of 1 or like a 0.5 or something, that is the most acidic. Okay, that's incredibly acidic. So acidic that it would be then corrosive. Up to pH scale of 14. So pH runs from 0 to 14. And here's how these pHs make sense. Anything of a pH less than 7 is going to be considered acidic. Now, the closer you are to 7, the less acidic it is and the more neutral it is, but we'd still classify a pH of like 6.5 as acidic, right? But that's like barely acidic. Okay, a pH of 2 is really, really acidic. So the lower you go, the more acidic you become. Okay, so anything above 7 is considered basic. So 7.5, we do consider that basic, but barely. That's like pretty neutral still. Okay, so pH of 14 would be the most basic. And then it gives you a bunch of stuff here, different substances and their acidities, things you might come into contact with. It also shows you how Look at this right here, how concentrations of H plus and OH minus are changing in relation to one another. As one decreases, the other increases. And that makes sense, right? Because those multiplied by each other give you a constant, Kw. So if the multiplication of these concentrations give you constant, then as one increases, the other has to decrease to keep it constant. All right? So it also relates concentration to pH. So you could look at any of these concentrations and how concentration of H plus relates to pH. Okay, any questions on pH scale and the numbers and how to know if it's acidic or basic? All right, let's keep going. I actually already addressed this. What if your pH isn't 1 times 10 to the minus? What if it's something else, 2 times 10 to the minus? You just put it in your calculator. You can't write today. So again, if it's 2.3 times 10 to the minus 6, well, we'll know it'll be around a pH of 6, but it's not going to be pH of 6. So what would you get? Negative log of 2.3 times 10 to the minus 6. 5 point something. Anybody get it? 5 point. Autumn got 5.6. Okay. So you can always look at your exponent and say, okay, if I'm determining concentration of H plus here, then it should be around what my exponent is, but it's not going to be exactly your exponent, be around it. So you need to calculate it for sure. Okay, questions on pH thus far? Does that make sense? So good, so far so good. All right, now what if I give you a solution of an acid or a base? Can you calculate pH? So here I'm not telling you what your H plus concentration is. You have to determine what H plus concentration is. Because pH is the negative log, not of HCl, of H plus. So how would we determine the concentration of H plus here? Well, the first thing you have to do is say, okay, what kind of acid is this? What kind of acid is HCl? Is it strong or weak? All right, Keegan said it's strong, that's right. So it's a strong acid. So what do strong acids do? They completely dissociate into H plus and Cl minus. So when we say we have a 1 times 10 to the minus 6 molar solution of HCl, that means we have really none of this, and we have all products, 1 times 10 to the minus 6 molar of each of our products. Okay, so we actually do know the concentration of H plus but this is only for strong acids. We can't do this for weak acids because weak acids only partially dissociate. So we'll still have some of the concentration of the weak acid, but for strong acids, they completely dissociate. So how would we get the pH? Well, negative log of the concentration of H plus. And we know when our base number is 1, we can just look at the exponent. So what is our pH here? Yeah, just 6, okay? But here we're not given a 1 times 10 to the something. Here we actually have to calculate it. So we're just going to assume the same thing since it's the same acid and we know it's strong, that the H plus concentration is equal to the concentration that we're given in the problem, 4.5 times 10 to the minus 4 molar. So we just take the negative log of this. And the pH is equal to what? Should be somewhere between 3 and 4. 3 point, okay, Kayla got it, thank you. 3.5, great. Okay, questions? So here we had an added step because I'm not giving you concentration of H plus directly, I'm giving it to you indirectly. Okay, what about if we have a different kind of a solution, KOH? What is this? This is not even an acid. This is a base. What kind of a base is it? You guys should recognize OH minus here. This is a strong base. but I'm not asking for POH, I'm asking for pH. Okay, so do you guys remember the equation I wrote earlier? There's a simple way to solve this. 14 equals pH plus POH. Did I write that earlier? Did we write this earlier? I can't remember if I wrote this earlier. I told you how to solve for POH. I know I wrote that earlier. And I know I wrote what pH is earlier. But I want you to know this equation that pH, the combination of pH and POH is equal to 14, the max on the pH scale. Okay. So there's a simple way to go about this. Because we have a strong base, we can easily calculate the concentration of POH because we know strong bases do the same thing as strong acids. KOH will completely dissociate into K plus and OH minus. So we're going to have none of this, and the concentration, we're told, actually corresponds to all products. So if we're solving for pH here, we know we have 14 right here. Why don't we just get POH and then we just subtract that from 14? That's the easiest way to go about this. So what is POH? Equals negative log of 1 times 10 to the minus 3. And because our base number here is 1, we can just look at the exponent, right? So POH equals, not negative, it's just positive 3. Yeah, pH will never be negative, by the way. Nor will pH, always be positive numbers. So now pH equals 14 minus POH. The other way, Danielle said, I don't understand how you need to use that formula. Well, it's just like any other equation, okay? I'm not deriving the equation for you, but I'm introducing it, okay? And I'm showing you how to use it, okay? There's actually 2 ways you could solve this. I'm going to show one more way real quick, Danielle, and I'll come back to this equation. You could also solve it using KW. Okay, we already introduced KW. We know KW is the concentration of H plus times the concentration of OH minus. So if you don't like this whole pH, POH thing, you could plug in 1 times 10 to the minus 14 for KW, and you could plug in 1 times 10 to the minus 3 for your OH concentration because we're told it's a strong acid and we know OH concentration is going to be equal to what we're given in that problem. And so then you could just divide KW by this 1 times 10 to the minus 3 to get the concentration of H plus. And then we know pH equals negative log of the concentration of H plus. Okay, so there's another way. So you just ignore potassium. Oh yeah, ions, those things don't affect your pH. Okay, H plus or OH minus are what you're concerned with here. I'm about to sneeze. Excuse me. So the ones we worked before this were asking for POH. Alexis, let's go back and look. No, is asking for pH. What is a pH? The whole time here, we're solving for pH. It's just that we're given acids up here, and we know we can directly get the concentration of H plus from an acid because acids disassociate to give H plus. Bases don't do that. Okay, bases generate OH minus. And so we had to indirectly get pH from OH minus, all right? And that's why I introduced this equation where 14 equals pH and POH. Because just because I have a base here, I don't know the concentration of my H plus unless I were to do some work over here with KW and solve for it. Danielle, does that, I don't know if that answers your question. How did I know to use this formula? Well, I know it's the simplest way to get pH because it's relatively simple to determine the concentration of OH minus here, knowing that I have a strong base. Not really, but you can keep going. Okay, we're gonna do some more practice with it. Just definitely, here's the deal. What we did in the little review session I just had, we made a whole list of equations. Because obviously, by the time we get to the end of chapter 10, you've got a lot of equations, like a whole profile of them. I would get a blank sheet of paper and just write down all your equations. Okay, go to the end of when I post the recording later today. Go to the end of it. We write down all the equations from chapter 9 and 10 that are you're gonna need for the exam, and this is one of them. Okay. All right, so we're gonna put that on pause for just a second. We're gonna still talk about pH, but what if we are given pH and we want to know the concentration of H plus? Why would we ever want to know that? Well, in the body sometimes, okay, we know pH of our blood or whatever, and we may need to know the concentration of various ions because our blood has ions in it. We call them electrolytes. So there would be times, especially if you're going into certain health professions, where you would need to calculate the concentration of H plus as it relates to like your blood. And by the way, what I'm about to say, if it doesn't click well, you can rewatch it with this link right here. It's a very short YouTube video, and you have the slides, so you could copy and paste this. So how do you solve for H plus? We have to undo the pH. Okay, how do we undo the pH? Same equation, pH equals negative log of H plus. Here's your steps. Number one, move the minus sign over. So now this becomes negative pH equals log of the concentration of H plus. Secondly, we need to take the antilog. Right? How do you do an antilog? What you do, antilog is 10 to the power of x. And I don't actually mean x. I mean x is referring to whatever we have in our equation. So we're gonna make everything an exponent. We're gonna do 10 to the power now of negative pH, 10 to the power now of log of H plus. And what that does, when you have a log written in, it undoes the log. It like cancels it out. Okay. So that leaves us with the concentration of H plus on the right side of the equation. So concentration of H plus, since we've gotten rid of the log now, is just equal to 10 to the power of negative pH. Okay, so for sure on an exam, I will ask you to solve for pH, and then I will give you a pH, and I'll ask you to solve for the concentration of H plus. So know it both ways. Let's put this into practice. If a solution has a pH of 8, what is the concentration of H plus? So you say, okay, 10 to the negative pH, which is 8, which equals 1 times 10 to the negative 8, all right? And that is my concentration of H plus, and that's units of molarity. Yeah, I'm going to go back. So once you do the antilog, it undoes the log here, but we still have the base 10 on the other side of the equation. So we have to keep that because we don't have a log on the other side. All right. So we have 10 to the, now this becomes an exponent to the negative 10 to the negative pH. So anytime you're given a pH, you can plug that in as your exponent. And in your calculator, you'll type in 10 raised to the power of negative. Don't forget the negative because we moved the minus sign over. All right. Because we're just trying to isolate H plus. We're trying to solve for the concentration of H plus. So the example here we worked, if we have a pH of 8, we do 10 to the negative pH, so that's 10 to the negative 8, which is just 1 times 10 to the negative 8, all right? Literally, if you plug that in your calculator, that's what you should get. Now, the moment that you don't have a nice whole number, if you have like a decimal, so look at the next problem, pH is 4.5. Here we don't have a whole number. 10 to the negative pH is going to be 10 to the negative 4.5. You cannot leave it this way. We can't leave decimals in our exponents. Whole numbers are fine. That's why the problem previous 10 to the negative 8 is just our answer. But here you actually have to put this in your calculator. When you do it, do a 10 to the negative 4.5. to the power, what do you get? It changes it, right? It gives you a number with a whole, it gives you a number, and then you have the exponent, and your exponent should be a whole number. Okay, Kendall says 3.16 times 10 to the negative 5. You see how it gives you a different answer, but this time your exponent is a whole number. So if you're ever given pH as a decimal, you've got to plug that in and calculate the true value. It's not that this is not a true value. It's just we're expressing it in a different way. And we say this is our concentration of H plus. Okay, another practice problem. If you have a pH of 12.3, here I'm asking you, not H plus, what is the concentration of OH minus? Kirsten, so H plus is the exponent or the entire thing? No, H plus is not the exponent. pH is the exponent. You see how it says pH is 4.5? And that's what we're plugging in as the exponent. It's the pH. And then we're solving for the concentration of H plus. But your answer for what the concentration is this whole thing. So the answer is 3.16 times 10 to the minus 5. Yeah, it's the whole thing. Can I go back up to the equation? Concentration of H plus equals 10 to the negative pH. You good, Keegan? All right. So let's do one more, but this is different. Okay, how is this different? We're not solving for H plus, we're actually solving for the concentration of OH minus. How are we going to do that? Well, again, that equation I mentioned earlier, 14 equals pH plus POH, okay? pH plus POH equals 14. This is going to be the easiest way to do this. Danielle, I want to go back to your question earlier, like how do I know when to use this equation? Anytime you're given the P of H, which is indicating hydrogen ions, but you're asked for information about OH minus, this is the best equation to use because it involves both H and OH minus. Okay, so for example, if I were to give you a POH and ask you what is the concentration of H plus, that'd be just the opposite of this. I'm including both OH minus and H plus, right? So this equation combines both of those terms, so that's when you know to use this one. Let's work this out and see if this makes sense. I know my pH, so I'm going to literally plug in. Okay, so 14 now equals 12.3 plus POH. So how do I solve for POH? Subtract, right? So 14 minus 12.3, you should get 1.7. Thank you, Lucy. That equals POH, all right? So how do we get OH minus concentration from POH? Well, how have we been getting H plus concentration from pH? You do 10 to the negative POH in this case. We were doing 10 raised to the negative pH to get the concentration of H plus. Same thing with OH minus. We'll do 10 to the negative 1.7 will equal concentration of OH minus. Okay, what we're saying is 10 to the negative POH equals concentration of OH minus. And we now just calculated POH. Why do we turn it negative? Kiara, that goes back up to this. When we were undoing this equation, we have this, I'm going to zoom in, we have this negative sign here on the log, okay? Because pH is the negative log of the concentration of H plus. So if we're trying to isolate just H plus, the first step was to move the minus sign over, okay? So if pH equals the negative log of the concentration of H plus. If we move the negative over, essentially divide by a negative sign on both cases, it gets rid of the negative on the right side of our equation, and we can erase that, and it makes pH negative. Same idea if we had POH, right? We know POH equals negative log of OH minus. So we move the minus sign over, and it undoes it on this side. So that's why we have that negative when we do 10 to the power of the exponent. That negative doesn't go away. We still have to account for it. Okay. So what is 10 to the power of negative 1.7? What is our concentration of OH minus? No problem at all. Okay, yeah, 0. Oh, I'm on eraser. 0.02 molar. Okay. So questions so far on how I solve for the concentration of H plus or the concentration of OH minus, or how I calculate a pH or a POH. Okay. You could also use KW. I'm not going to take the steps to walk through this because you literally get the same answer. So I think knowing how to do it. I'm going to skip over this. We just don't have time. I'm not going to ask any questions about why it's a logarithmic scale. Whoops. Okay, I think I forgot to put this slide in your slides, or sorry, this particular problem. So I think you may not have this in your slides. So find like a blank sheet of paper or somewhere to work this. It says carbonic acid is part of our blood buffer system. What is the pH of a solution in which the concentration of this carbonic acid is 1.7 times 10 to the minus 3 molar? All right, what's the first thing we need to do? Step 1. We need to identify if this is a strong or a weak acid. Identify the acid. Is it strong or is it weak? Well, did I have the... Sorry, I'm trying to find the table. Okay, here's the table. And I actually already had it labeled from this morning. Carbonic acid is, look, the title of the slide says Ka values for what? Weak acids. So what kind of acid is this? It's a weak acid. And we are actually going to need the Ka value. So let's take that value, 4.3 times 10 to the minus 7. Let's take that back to our problem. So this is weak. You're weak. All right, and step number 2 is let's write out the dissociation reaction. Let's look at how this breaks apart. H2CO3. It's a weak acid, so we have a double arrow here. Makes what? HCO3 minus and H plus. Bicarb and H plus. Step 3. Write the Ka expression. You guys remember how we write a Ka expression for any reaction? Products over reactants. Concentration of products divided by concentration of reactants. So Ka for this will be equal to, here's our products, bicarb and H plus concentration of bicarb, divided by the concentration of H2 carbonic acid. Products over reactants. So you can already see solving for pH for strong acids is really simple. It was like a one-step thing. Solving for pH of a weak acid is a whole different ballgame because we don't know what extent it disassociates to. But Ka tells us. All right, so we said, what was our Ka value? We said Ka for this was 4.3 times 10 to the minus 7. All right, so we're about to plug that in. So we're given the initial concentration of H2CO3. So I'm going to highlight that. That's what we're given here, and that's what we're going to plug in right here. And then we're given, I don't know if y'all can see green. Can y'all see green? Barely. We're going to plug in K right here. Okay, we're going to plug these values in. So I'm going to move over a little bit. 4.3 times 10 to the minus 7 equals 4.3. That's what we now have. So we just plugged in the numbers that we were given. So the question here, what was the question again? The question is, what is the pH? What's our equation for pH? The first one I gave you. pH equals negative log of the concentration of H plus. In the chat, he said, how did you get K? I went to that table. This table right here. I just grabbed it off the table. Okay. So what portion of this equation here is going to allow us to solve for pH? This part, right? We want the concentration of H plus. Here's the one, you think of this as like some kind of a trick. It's not a trick, it's just, it actually makes logical sense to think, okay, anytime one molecule of carbonic acid breaks apart, I will get one of these and one of these, one bicarb and one hydrogen, right? So let's say 1,000 molecules of H2CO3 dissociate. I'll get 1,000 bicarb and 1,000 H plus. Let's say 1,000,000 molecules. I don't care how many. What I'm trying to illustrate to you is that the concentrations of these things will be identical. We can't get one without making the other. So we'll never have different concentrations of our products. So you know what that means we can do? We can call them the same variable. I'm going to plug in X for both of these things because X means it's going to be the same. And I'm trying to solve for H plus. I don't know what my concentration of bicarb here is. The problem didn't tell me. So I'm just going to plug, but I know my concentration of bicarb and H plus can be the same. So how does this impact our equation? What does our equation now become? So I'm literally just going to erase these things and plug in X. Don't erase yours if you've written it, just rewrite it. But X times X is what? X squared. I think you guys could solve it from here, couldn't you? How do we solve for X? Multiply both sides by 1.7 times 10 to the minus 3. That cancels. Now what do we do? Yep, Autumn said take the square root of both sides. 2 seconds. Okay. Whoa, what happened? Why does it do this? Come back. There it goes. Okay, take the square root of both sides. So step 4, I'm going to write a step 4. Step 4 was plug in X for products. All right, for both products. And then step 5 is rearrange and take the square root. Take the square root. SQRT reminds me of STBX. One time I used that in a text and somebody was like, what is STBX? Starbucks, right? Nobody thinks that's funny. Okay, solve for x. So how do we solve for x? So let's actually do this. In your calculator, do 1.7 times 10 to the minus 3 times 4.3 times 10 to the minus 7. Take the square root of the product of those numbers. What do you get? Somebody's going to beat me. Okay, you already did it. 2.7 times 10 to the minus 5. So that is x, right? Y'all took the square root. So we solved for x is 2.7 times 10 to the minus 5. Now, why is x a big deal here? It says units of molarity. X is H plus. We said we plugged in x for both of these things. And guess what? How do we get pH? We wrote it up here. pH is the negative log of H plus. Now we can get pH. So the last step, step 6, solve for pH by taking the negative log of what x was, which is the concentration of H plus, right? What do y'all get when you do that? Haley got 4.56. Great, thank you, Haley. pH equals 4.56. Whoa, that was a hard problem. But you can do it. Expect one of these on the exam, just one, okay? You can do it one time. Okay, questions on this? Some of you have some looks right now on your faces. My brain hurts. But we wrote out the steps, nice and neat. I usually don't even do that, okay? All right, on to buffers. That's pH, on to buffers. Okay, what is a buffer? It is a combination of substances in a solution that act together to resist changes in pH. Anybody ever played the game Resistance before? It's kind of like Mafia, but different. It's really fun. Anybody ever played Mafia before? Come on, tell me you get out and play games. I like games like that. Probably because I'm very competitive. Okay, buffers, back to buffers. It's crucial to maintain proper pH in biological systems and in laboratory settings. I don't think I spelled that right. Maybe I did. So in laboratory settings, when you make solutions, I used to make these in grad school all the time. I can't tell you how many hours of my life I spent standing at a pH meter. All right, you got to have proper pH. And in biological systems, our bodies are made up of buffers in our cells and all kinds of things. So you got to keep constant pH. So it's usually a weak acid and it's conjugate base. Okay, so you guys remember how to identify a weak acid and a conjugate base? Can you label that on this next equation? Which one's the weak acid? Nobody? Thank you, Grayson. Conjugate base would just be once you give away the hydrogen, what's left over. Okay. So, like for example, acetic acid. Here's your weak acid. Here's your conjugate base. So let's consider acetic acid for a minute. This is a buffer. We're going to draw a diagram for how buffers work. So this is what buffers are and what they do. They resist, they want to maintain pH. So how do they work? Well, first off, what things could affect pH? Okay, acids affect pH and bases affect pH. Okay, why do acids affect pH? Well, I'm going to draw something on the top here above this line. I want you to keep this in mind. H plus, acids generate H plus. The more H plus you have, the larger the concentration of H plus, the lower pH, the more acidic your pH. Low pHs are acidic pHs. And that directly correlates to the concentration of H plus. The more you have, the lower your pH. Carrie, yes, just 1 second. Or Carrie, sorry. And then when it comes to OH minus, okay, which is what bases usually generate, the more OH minus you have, the higher the pH goes, the more basic your pH becomes. Okay, so this is acids, do this, bases do this. Okay, so keep those trends in mind. Is that good? Is that good, Kiara? Do you need me to go up any further? Okay. All right, so acids and bases, these could threaten to change pH, to raise or lower, and buffers, biological systems, don't want that to happen, okay? It's very important that we keep our blood pH around physiological pH, 7.3, 7.4. So how does this work? I'm going to draw this diagram. You need to know how this works. We have our buffer system in equilibrium, and I'm not drawing in water or anything else right now. I'm just drawing in the weak acid and the conjugate base components, and they're in equilibrium in a buffer. You have relatively equal amounts of conjugate base and weak acid. So let's say we add a strong base, such as NaOH, all right? This could threaten to raise our pH, but the buffer says, no, I'm not going to let that happen. How is it not going to let that happen? Which component of our buffer could neutralize NaOH? Do you think an acid would neutralize? This is a base. So do you think acids neutralize bases? This is the conjugate base. Or do you think bases neutralize bases? Yes. Wait. Okay, we get both answers. Acids neutralize bases. Okay, I'm going to make that a point here. Put a star by it. Acids neutralize. I said acids, I promise. Acids neutralize. Sorry, everyone. Probably getting a phone call for my birthday. I'm in class. All right. Turn my phone on airplane mode real quick. So acids neutralize. So this weak acid here sees this NaOH, and they're going to react together. Okay, so what is the acid going to do? It's going to donate its hydrogen. It's going to donate its hydrogen to OH minus, right? So we have OH minus from the base, from NaOH. These two are going to react. What are they going to make? Make water. Water is neutral. That's why we say it neutralized it, okay? So we just neutralize the base by making a neutral product, water, okay? What else do we generate? In the process, we create more A minus. So I'm gonna make a note here. When bases are added, the concentration of HA gets used up a little bit because it's reacting with the NaOH. So the concentration of this goes down, okay? Because it's working to neutralize the base, all right? And the concentration of A minus goes up because we make more of that in the process. All right, let's look at strong acids. If we add an acid such as HCl, HCl is going to generate H plus, right? It's going to disassociate and make H plus in solution. And this could lower pH. The more H plus we have, the lower pH goes. So what do you think neutralizes acids? Do bases neutralize acids or yeah, that's exactly right. So this conjugate base sees that and it's attracted, okay? And what are those going to make? Look what those are going to make. When you combine A minus and H plus, you make more of your weak acid. So bases acids. I'm actually going to pull that right down here. So point number 2 is that when are added to a buffer system, the concentration of A minus goes down, concentration of HA goes up. We make more of it. We use up our conjugate base to neutralize the acid, and in the process, we make more weak acid, okay? Now, the reason this doesn't affect pH is because weak acids only partially disassociate. They don't disassociate very much. So it's not going to affect the pH very much, the way a strong acid would. And it's going to maintain a relatively constant pH. It might affect it a little bit by like 0.01 or 0.1, but not much, okay? We're actually going to look at some examples in a minute. So how much time do we have left? 20 minutes, roughly. I'm going to skip over this slide. I want to get right to our buffer problem. I just want to make sure we have time to finish it, okay? These are just conceptual questions, but I think we've really talked through them honestly when we explain the buffer diagram. By the way, is everybody good here? Can I scroll on? Bradley, what's too much? Okay, so now I've explained what a buffer is. We've talked about how it works. Now we're going to look at how do we find pH of a buffer system. That wasn't nice, Bradley. All right, we can find the pH of a buffer solution if we know the concentration of the acid and the conjugate base. All right. So we have our dissociation reaction here, our buffer equation. And I'm not going to derive this, but I just want you to know this equation right here that we use to find pH of a buffer, it comes from the equation for Ka of weak acids, all right? We derive it from that. But I'm not going to ask you to derive that. But here's our equation. This is going to be a very important equation on exam 4. So write this down on your list of equations and know how to use it. And know that this is only for buffers. If I ask you what's the pH of a solution of HCl, you don't have a buffer, do not use the Henderson-Hasselbalch equation, all right? So that's the name of this equation, and it's this, pH equals pKa. What's pKa? We talked about that at the very beginning. pKa is just the negative log of a Ka value, which we have a table of Ka values. So pH equals pKa plus the log of the concentration of, what is A minus? This is the conjugate base divided by the concentration of the weak acid, okay? All right, there it is. Let's put it into practice. Okay, I have that same equation down here if you're still writing. There it is. Oh, this is another slide I got to skip over for time's sake. So there's some qualities I was going to tell you about, but okay, here's our equation again. Oh crap, I forgot how many slides we have. I don't have time for this either. This is the slide I want to get to. All right, so skip ahead till you find this page. We're going to work a buffer problem. A buffer problem has 3 parts. So the first part is you're just calculating the initial pH of the buffer. When do we not use it again? You don't use it if you don't have a buffer. So like if I were to ask you, what is the pH for a solution of HCl? Okay, we did an example of that earlier in lecture day. A solution of HCl, that's just a strong acid. okay? Buffers are made from weak acids. So you would just use pH equals negative log of H plus, all right? The equation for pH we used earlier. You only use Henderson-Hasselbalch when you have a buffer. All right, so here we have a buffer. It says, what is the pH of a buffer solution? It'll tell you when you have a buffer. Made with 0.1 molar HF and 0.12 molar NaF, okay? We have to know, the first thing we need to identify, which one's our weak acid, which one's our conjugate base. Is HF the weak acid or is NaF the weak acid? What do y'all think? How do you know? Well, you could always look at what the K is for. We only have Ks for weak acids, okay? So it says K of HF. That's an indication. All right, HF is my weak acid. Plus, it's the one that has hydrogen. Acids have to have a hydrogen in them. An acidic hydrogen, not just a hydrogen bonded to carbons. All right, so if we're trying to solve pH, pH equals pK. So after deciding which one's the weak acid and which one's the conjugate base, now we need to calculate pK. Okay, so that was step one, identify those. Step two, let's get pKa. pKa equals negative log of 3.5 times 10 to the negative 4. So what is pKa? I forget what it was earlier this morning, 3.46 or something like that? 3.46. I think that's what we had this morning. 3.45. Did you round right? We're going to go through, I think it was 3.4. Is it 3.45? Somebody confirm. Okay, rounded to 0.46. All right, we're using 3.46. All right, now let's solve for pH. pH is just 3.46 pKa plus, not the minus log here, plus the log of the concentration of conjugate base on top. That is 0.12 molar because NaF is our conjugate base, divided by 0.1 molar on bottom. When you do that, you get negative 0.079. So 3.46 minus 0.079. .38. It's our initial pH. Know what y'all got? Somebody get the same thing? So ways people can tend to mess this up. One, they forget to calculate the pKa and they just plug in the Ka. Did I do it wrong? I think I did. Did I do the negative log? Should be plus. I might have had a negative in my equation. Okay, good. I think I did it wrong. 3.54. It should have been a positive 0.9. I may have had a negative or something in here. That's another way people can mess it up. What I just did, you accidentally put a negative log instead of adding the log. Okay. So that's step one for a buffer problem. Just plug in what you're given, calculate pK, plug everything in and solve for pH. Step two, we're going to now examine the pH of a buffer when we add one of two things. When we add either a strong acid or a strong base. Autumn said, how do we know if it's negative or positive? What do you mean? How do we know if what's negative or positive? The log part? The equation. Okay, I should have had a plus here, not a minus. But the other equation is pH equals negative log of H plus, right? This is not for buffers. So we're not using this equation here because this is just for a solution of a base or an acid, not a buffer. Okay, so sometimes people get tripped up because they're so used to things being a negative log in the other equation, and they put a negative log in this one, but in the Henderson-Hasselbalch equation, it's positive. So you just need to really examine your equation. That's how you should know what to use. And it all depends if you have a buffer or not. And your problem will tell you have a buffer. All right, so now we're going to add some NaOH. It says I'm going to add 0.02 moles of NaOH. All right, we have the same components. So here's the things that will always be the same. The components for your buffer, what your weak acid and conjugate base are, and your pKa is always going to be the same. So we're going to need pKa in a minute. I'm just going to rewrite it down here as 3.46, all right? Step number 1, calculate the molarity. Okay, look, we've got units of molarity here, and all of a sudden our units are different. We have moles. I don't need moles, I need all to be the same. So calculate molarity for either the acid or the base that we are adding to the buffer component. So molarity is this, 0.02 moles. It's moles per liter, right? We got 1 liter. So I will always give you the volume. It may not always be 1 liter. It could be 2 liters. It could be 500 milliliters. So just always divide by liters, which would be here 0.02 molar. Do not always assume that the number of moles is going to be equal to your molarity. It just so happens to be the case here. But the moment that your volume is not 1 liter, if it were 2 liters or again 0.8 liters or something, you won't get the same number in molarity. Okay, so always calculate that. All right, the next thing we're going to do is we're going to make something called an ICE chart. ICE chart. So what that looks like, we're going to write ICE down the left side, and we're going to calculate the changes in our our weak acid, which is HF, and our conjugate base, NaF, based on how the buffer is going to respond, right? We have added 0.02 molar NaOH. The buffer is going to respond to neutralize this. So what did we say earlier? When we add a strong base, what goes down and what goes up? We wrote notes on our buffer diagram. We said this goes down and this goes up. What goes down? The concentrations are going to change. We need to know what's going to decrease and what's going to increase. You guys remember? Go look at that buffer diagram. Hold on. Where's our buffer diagram? Right here. Okay, what do we say? I'm going to highlight it right here. We said these things are what I'm talking about. Okay, we have this scenario. We're adding a base, right? There we go. Thank you, Bradley. Okay, so let's go back down. Sorry, I got to scroll. Well, here we are. So that's going to be important right here when we plug in how the concentrations of things are going to change. Here's what ICE stands for. I is our initial concentrations, and the problem always gives that to you. Okay. Initially, we have I'm just looking at my problem. We have 0.1 molar HF. We have 0.12 molar NaF. So just plug those in. Now, how things change depend on what the molarity of the base, or if we're adding an acid, how much that is. So we said Bradley says in the chat right here, he's right, HA, which in this case, our weak acid is HF, right? HA is just a general example for any weak acid. Here, our weak acid is HF. So that's going to go down. So I'm going to put a minus sign there. NaF is going to go up. This is our conjugate base, which stands for A minus, okay? A minus is the conjugate base. Here, NaF is the conjugate base. So that's going to go up, so I put a plus sign there. That's how things are going to change. Now, they're going to change by how much? Well, we want to neutralize all the base, so they're going to change by 0.02 molar. This is why you have to use units of molarity. Now, we're just going to add up our columns. E stands for the new equilibrium concentrations. So 0.1 for HF, it's 0.1 minus 0.02. So I got 0.08. I just did 0.1 minus 0.02. For our conjugate base, NaF, it's 0.12 plus 0.02, so 0.14. And this right here is what you plug in to the Henderson-Hasselbalch equation. okay, which is given to you right up here. So that's the last step here. Step 3, plug in the new equilibrium concentrations. So we're solving for pH equals pKa 3.46 plus the log of what goes on top, what goes on bottom. Conjugate base goes on top, weak acid goes on bottom. And it's the new, you pull the numbers from your row E. So 0.14. Sorry, that's not legible. And 0.08. All right, now what is our new pH? So we're trying to see how good of a job did this buffer do. When we threw some NaOH into our buffer solution, or let's say you eat something that is acidic, anybody? Like, I just can't eat acidic foods because they mess with me. I've heard people say that. Okay, so our bodies are constantly responding to like the medications we take, the drugs that we eat, the food that we eat, okay? And they're doing this. So Tyler said pH, sorry, I didn't mean to move the slide. pH equals 3.88. That's different than 3.7. Anybody could confirm what they got? What did y'all get? 3.7? Lucy got 3.7? Bradley, you're overruled. Okay. So initially, what was our buffer pH? It was 3.54. And when we add some base, do you think pH stayed relatively constant? It raised to 3.7. Not bad, right? 3.54 to 3.7 is not a big change. So we see that our buffer did pretty good. Okay, questions on this. We're going to do part 3, where we look at what happens when we add an acid. And that's literally all we're going to have time for. I'm so sad. I'm like crying because we didn't even get to buffers in our biological systems. Maddie says, where did I get the E again? That's just part of the ice chart. So I stands for the initial concentrations, and those are always given to you in the problem. C is we're plugging in how much things are going to change by. And we have to first calculate the molarity of the component that's being added to the buffer system. Here, it was a strong base. Okay. E is just the sum of these things. Okay. That's how we got that. We're just literally adding up these things to get E. Okay. Places where people constantly, okay, the chat, coffee and chem lecture don't mix. Yeah, they do. I love drinking coffee while I'm lecturing. Are you going to make videos of the rest of the slides? My brain is racing. Okay. Kiara, no. I mean, we're going to do this one right here, and then anything else, this is the sad part, buffers in the body. We're not going to have this, we're not going to have this on the exam. I don't feel right giving y'all like another 40 minutes, hour-long lecture material just for over the weekend when you have an exam on Tuesday, okay? So, unfortunately, I'm really sad about it. We just don't have time. Okay, it didn't work out. All right, let's look at this last one before we run out of time on this. Okay, what is the pH of a 1 liter buffer solution when you have 0.1 molar HF? So look, same initial concentrations, okay? And add 0.02 moles this time of HNO3. You know what? I'm gonna change this up because I want to. 0.05 moles. I just don't want you to think it's always going to be the same. And I'm going to say, what happens if we have like 0.8 liters? Okay. You have to always calculate molarity. All right. So now, because I changed the numbers, which I totally could do, what is your molarity? Well, we're going to do 0.05. Molarity is moles per liter. So moles of HNO3 divided by 0.8 liters. What do y'all get when you do that? Kendall got 0.0625 molar HNO3. So this is how much, and this is a strong acid. If you were to go look at the table for strong and weak acids, the one with the big red and blue arrows that run opposite ways, you would see this is a strong acid. Now we're going to plug this into our ice chart. So we have the concentration of HF, concentration of NaF. Initially, it's 0.1. These numbers, the initial numbers, will always be the same. And you want units of molarity, not moles. Okay, this is molarity. Now we're going to plug in this as our change. When you add a strong acid to your buffer system, that's what we're doing here. What goes up and what goes down? Remember, go look at that buffer diagram. Your buffer components respond to neutralize. Here, we're neutralizing a strong acid. What goes up, what goes down? This is going to tell us how to put what plus and minus signs on what column. A goes up, HA goes down. Okay, so I'm going to put a minus sign. Wait. Hold on. I think that's backwards because that's what we did last time. It's different. We're adding an acid, and the conjugate base is going to be used up to neutralize the acid. It should be the opposite of this. It should be that this is going to go down and this is going to go up. A is the conjugate base, all right? So 0.0625 molar and 0.0625 molar. Okay, you see how these minus signs are opposite what we had up here? We had a minus and then we had a plus on the conjugate base. We had a minus on the weak acid. Here it should be opposite because we're adding the opposite thing. We were adding a base earlier, now we're adding an acid. So then you add these up. 0.1 plus 0.0625 is 0.1625. Okay. 0.12 minus 0.0625 should be 0.0575. Is that right? Is that what y'all got? Then we take these concentrations and we plug them in. Step 3, plug them into our pH equation, which is right here. pH equals pKa. Same pKa through all 3 parts, and it was 3.46 last time, so it's still 3.46 because we're dealing with the same weak acid, plus the log of what? What goes on top, what goes on bottom? Conjugate base always goes on top, so that's 0.0575 molar divided by 0.1625 molar. Yet, Autumn, yet. You could not do one yet. Okay, I know stress levels are probably high right now. We need to calculate. Bradley said he got pH equals 3.01. Is that what you got? That completes a buffer problem. So take a deep breath, okay? All this is going to, I promise, if you will show up Monday or watch my recording, I'm going to work like 2 of these things, 2 more times. Y'all's faces right now. I'm sorry, this is a lot. I know it's a lot. What time Monday? Okay, I'm gonna do one review at 8:30. I'll send an email tomorrow on what time. One at 8:30, one at 10. And we are gonna practice pH. We are gonna practice buffers, okay? We're gonna practice all this stuff. So here's what I want you to do today.